Have you ever stopped to wonder how an AI can tell the difference between a picture of a cat and a dog? Or how it can become a grandmaster at a game like chess? Well, it's definitely not magic. It's all about learning. You see, at its very core, artificial intelligence is really just a massive attempt to get machines to learn, think, and solve problems in the same ways that we humans do. All right, let's dive right in. So that really brings us to the million-dollar question, the one that drives this entire field. How in the world can we get a machine to actually learn like a person? This is the central challenge. And it turns out there isn't just one answer. There are several really brilliant approaches, and each one mirrors a different facet of our own intelligence. Okay, first things first, let's get our main definition straight. When we talk about AI, we're talking about the simulation of human intelligence in machines. The whole goal is to program them to think, to act, and most importantly, to learn in ways that look a lot like how our own minds work. This is the foundation for everything we're about to cover. So AI really splits into two big camps. On one side, you have rule-based systems. Think of it like trying to write a giant instruction manual for every possible situation. As you can imagine, the world is way too messy for that to work for everything. So we're going to focus on the other path, the more powerful one, data-driven machine learning. And here's the cool part. Instead of giving the AI a rulebook, we just give it tons and tons of examples and let it figure out the rules for itself. So let's start with the most familiar way of learning, from experience. For this whole section, I want you to think of the AI as a student, just trying to absorb information and find the patterns inside it. Now, even as a student, our AI has two very different study habits. First, you've got supervised learning. This is like studying for a test when you already have the answer key. All the data is neatly labeled. Then you have unsupervised learning, which is more like being dropped in a massive library and told, good luck, go find something interesting. Let's dig into supervised learning first. With this method, the algorithm is fed a huge data set where every single piece of information is already labeled with the correct answer. It's explicitly told, this is a cat, this email is spam, this house sold for this exact price. It's basically learning with a teacher, constantly looking over its shoulder and giving it the answers. And this approach is incredibly useful. If you need to sort something into a specific box, like spam or not spam, loan approved or loan denied, that's a classification problem. But if you're trying to predict an actual number, like the future price of a house, that's called a regression problem. Both are really powerful ways to make predictions based on data we already have the answers for. Okay, now let's flip to the other side of the coin, unsupervised learning. Imagine just dumping a massive, messy, completely unlabeled pile of data in front of an AI. No answer key, no teacher. Here, the algorithm's job is to play detective and sift through all that chaos to find hidden patterns and structures all on its own. So what kind of detective work are we talking about? Well, a few key things. First is clustering. You know how your streaming service just seems to know what shows you'll like? It's grouping you with other people who have similar tastes. Then there's dimensionality reduction, which sounds complicated, but it's really just about cutting through all the noise to find the signals that actually matter. And finally, there's association, which finds those weird but true relationships, like the classic example of people who buy diapers also being very likely to buy beer. All right, so learning from a textbook is one thing, but what about learning by getting your hands dirty? You know, through pure trial and error. This brings us to our next major category, learning by doing, where the AI is less of a student and more of an explorer. This is the world of reinforcement learning. And honestly, the best way to think about it is like playing a video game for the very first time. Our AI, called an agent, tries an action in its world. If it's a good move, it gets a reward, a point. If it's a bad move, it gets a punishment. Now, just imagine doing that millions of times, and you can see how it would eventually figure out the perfect strategy to win. This feedback loop is the engine that powers the whole thing. It's a really simple, powerful cycle. The agent acts, the world reacts, the agent gets feedback, and then it updates its strategy. It's just a continuous process of acting and adapting, all driven by a single goal: get the highest score possible. And where do you see this in the real world? In some of the most dynamic and complex fields out there. Teaching a robot how to walk, for instance, or building an AI that can beat the world's best Go player, or even setting airline ticket prices that change from minute to minute. All of these rely on this powerful trial and error approach. Now, there's a fascinating cousin to reinforcement learning called evolutionary algorithms. They also learn by trial and error, but they take their inspiration straight from biology.
Instead of having one AI learn over time, you create a whole population of solutions. Then you let them compete. The best ones survive and get to reproduce, mixing and matching their code to create the next generation, until the best possible solution evolves. It's literally survival of the fittest for computer code.
So we've talked about mimicking the process of learning, but what if we tried to mimic the structure that does the learning, the brain itself? This brings us to our third big approach, the AI as an architect, literally building an artificial brain. This is the realm of deep learning. It uses what are called artificial neural networks, which, you guessed it, are modeled after our own brains. But here's the absolute game changer. With other methods, a human has to tell the AI what features in the data are important. With deep learning, the networks figure out what's important automatically, just from the raw data. That is a massive deal. A perfect example of this is how an AI learns to recognize a face. You feed it a picture. The first layer in the network might just learn to see simple things, like basic lines and edges. The next layer takes those edges and learns to combine them into shapes, like eyes and noses. And the final layers put all those pieces together to recognize a complete face. It builds complex understanding from simple parts, layer by layer, all on its own. And just like our own brains have specialized areas for vision and language, there are different architectures for these artificial brains. CNNs are absolute wizards with images. RNNs are masters of things that happen in a sequence, like language or music. And transformers, well, they're the powerhouses behind amazing language models like ChatGPT. Wow, okay, so we've covered a ton of ground here. We've seen AI as the student, the explorer, and the architect. So now it's time to put it all together. The single most important takeaway is that none of these is the best method. They're all specialized tools, and it's all about picking the right mind for the job. Think of this as your practical cheat sheet. If you have clean, labeled data and need to predict something, you're going to want supervised learning. If you have a messy pile of data and need to find the hidden patterns, that's a job for unsupervised learning. For anything that requires real-time decision-making, like a robot or a game, you need reinforcement learning. And if you're dealing with really complex stuff like images, audio, or human language, you bring in the big guns, deep learning. So, from the student with an answer key, to the explorer learning from its mistakes, to the architect building an artificial brain, what we're really doing is creating machines that mirror our own diverse ways of knowing the world. And that leads us with one last fascinating question to think about. We've taught machines to learn like us in so many ways. What truly human skills should we teach them next?